Okay, in this video I want to look at the notion of a unit of a ring and a zero divisor of a ring. So let's just see what the definitions are. So if you've got two non-zero elements in a ring R, those are said to be zero divisors if you can multiply them together to get zero. And so this doesn't make sense from a normal calculus type setup because we're always dealing over the field of real numbers where we know if A times B equals 0, either A is 0 or B is 0. But if we're inside a ring, this is possible. And when that happens, they're called zero divisors. Next, we say that A is a unit if it has a multiplicative inverse. So I want to look at some examples real quick. So let's go inside of Z12 maybe, and let's see what the units are and then what the zero divisors are. So let's first look at the units. So from what we know from group theory, we know everything inside of Z12 that has a multiplicative inverse is everything that has a GCD of 1 with 12. So that means our units are going to be 1, the next one will be 5, the next one will be 7, and then the next one will be 11. And, you know, we can check that just real quick. Notice that 5 times 5 is equal to 25, which is equal to 1. And so that shows us that 5 inverse is equal to 5. And then similarly, 7 times 7 is equal to 49, which is equal to 1. And so that tells us that 7 inverse is equal to 7. And also 11 inverse is equal to 11. And so in fact, everything is its own inverse in this ring. Now another thing that we can check is that these are not zero divisors. And you can actually check that no unit is a zero divisor, but let's just check it for these cases real quick, and then later in this video we'll prove that if something is a unit, then it is not a zero divisor, and vice versa. And we can check that by doing a multiplication table with 1, 5, 7, and 11, and every other element from Z12. And so I'm not going to do that in its entirety, but notice if we do 5 times 1, we get 5, we do 5 times 2, we get 10, 5 times 3 is equal to 15, which is equal to 3, 5 times 4 is equal to 20, and then 20 is equal to 8. 5 times 5 is 25, which we already said that was 1 in Z12. 5 times 6 is 30, and then we know 30 is equal to 6. 5 times 7 is equal to 35, which is equal to 11. And then 5 times 8 is equal to 40, which is the same thing as 4. 5 times 9 is 45, which is the same thing as 9. 5 times 10 is 50, which is the same thing as 2. And then finally, 5 times 11 is equal to 55, which is the same thing as 7. And so now notice we never get 0 as an output of multiplication by 5. And so that shows us that 5 is not a zero divisor. And then similarly, you can show that 7 and 11 are not zero divisors by this like brute force method. Now you might say, well, what are the zero divisors? Well, the zero divisors are going to be everything else. So in other words, everything that is not a unit. So let's look at those. So obviously there's going to be much more of those. So we'll have 2, 3, 4, 6, 8, 9, 10, and then that's it. Okay, great. And now how can we check that? Well, notice that these come in pairs. 2 times 6 is equal to 12, which is equal to 0. 3 times 4 is equal to 12, which is equal to 0. Let's see what else we have. We have 6 times 10 is equal to 60, which is equal to 0. Great. And then finally, 9 times 4 is equal to 36, which is equal to 0. And do that covers all of them? Yeah. Okay, good. So this shows that these are all zero divisors. And so we partitioned Z12 into units and zero divisors. Now I'm going to clean up the board and I want to prove something about Zn in general about its units and zero divisors. So motivated by our example, let's look at the following observation. So M in Zn is a unit if and only if the GCD of M and N is 1, and then M in Zn is a zero divisor if and only if their GCD is not equal to 1. Okay, so let's prove this first statement first, and let's do the forward direction. So let's go ahead and suppose that M in Zn is a unit, okay? So what that tells us is that there exists some x in Zn such that M times x equals 1, and this is all happening in Zn. But what that means, that equality in Zn is the same thing as the congruence. Mx is congruent to 1 mod n. In other words, n divides mx minus 1. That's the definition of congruence mod n, which is the same thing as saying that ny equals mx minus 1 for some y in the integers. But notice what that gives us is this nice equation, which is minus mx plus ny equals 1. Okay, good. But from elementary number theory, we know that all linear combinations of m and n, and this is a linear combination of m and n, are multiples of the GCD of m and n. So what this tells us is that 1 is a multiple of the GCD of m and n. In other words, 1 divides the GCD of m and n. But if 1 divides the GCD of m and n, then 1 is the GCD of m and n, which is exactly what we wanted to show for this direction. All right, I'll clean up the board and we'll do the reverse direction. So now we're ready for the reverse direction. So going in reverse, we want to suppose that GCD of m and n equals 1. But now we're going to arrive very, very quickly at kind of something that we just had, and that implies that there exist integers x, y, and z such that mx plus ny equals 1. Okay, so we could get those from the extended Euclidean algorithm if we knew exactly what m and n were. I've got a video on why this kind of thing exists. You can look for it in the number theory playlist. But now we can rewrite this a little bit. Notice this is the same thing as mx is equal to minus ny plus 1, or mx minus 1 is equal to minus ny. In other words, n divides mx minus 1. Okay? But if n divides mx minus 1, that's the same thing as saying that mx is congruent to 1 mod n. But that congruence is the same thing as saying that mx is equal to 1 inside of Zn. So in other words, m inverse is equal to x in Zn. In other words, m is a unit. So m is a unit. Okay, so we've proved both directions of this first claim. Now let's move on to the second one. Okay, so now let's look at the second claim. So we're going to suppose that m in Zn is a zero divisor, and that the GCD of m and n equals 1. So in other words, we're working towards a contradiction. Okay, so since we have a zero divisor, So that tells you that there exists some a which is not equal to 0 in Zn with m times a equal to 0 inside of Zn. So that's what it takes for m to be a zero divisor. And then the GCD of m and n equals 1. So that tells us that there exists x and y in Z such that mx plus ny equals 1. Okay, great. Now, the next thing that we want to do is multiply this whole equation by a. But before we do that, notice that MA equals 0, that's happening inside of Zn, which is the same thing as saying MA is congruent to 0 mod n, or in other words, n divides m times a. Okay, great. So now we're going to go ahead and multiply this entire equation by a. And that's going to give us MA times X plus N times AY equals A. Okay, good. But now notice that N divides MA, N obviously divides N, so that tells us that N divides the left-hand side of this equation, which tells us that n also divides the right-hand side of that equation, which is a. But now, if n divides a, that's exactly the same thing as saying that a is congruent to 0 mod n, or that a is equal to 0 inside of Zn. Okay, but that contradicted this assumption right up here. Okay, great. And so that proves this forward direction of this second observation. So I'll clean up the board and we'll look at the reverse direction. So now we're going to look at the reverse direction of this second statement. And in other words, we want to suppose that m is in Zn with the GCD of m and n equal to d, which is not equal to 1. So what that tells us is that there exists some a in Z with a is strictly between 1 and n, and a times d equals n. So let's talk our way through that. Well, notice that D is a common divisor of m and n. In other words, it is a divisor of n. But being a divisor of n is exactly the same thing as this statement right here. Okay, so now let's talk about the inequalities in this case. So if a were equal to 1, then that means that D would be equal to n, which means that m and n would have to be the same thing, which would tell us that m was actually 0 in Zn. If a were equal to n, that would tell us that d was equal to 1, which is something that we also didn't assume. So that's why we have this strict inequality here. Okay, great. So now we're going to do a pretty similar thing that we've done in the last couple of arguments, which is find integers x and y with mx plus ny equals d. So in other words, write the GCD as a linear combination of the two numbers. And now we want to take this equation and multiply it by a. And so that's going to give us a times mx plus a times ny equals a times d, which is equal to n. Okay, great. Now we're going to move some things around. Notice that says that ax times m is equal to n times 1 minus ay. So I've factored some stuff out there. But then this right-hand side is congruent to 0 mod n, which we can rewrite as ax times m is equal to 0 inside of Zn. Okay, great. So let's see what we have going on here. We have m, which is not equal to 0 in Zn, and then a is not equal to 0 in Zn from this rule right here. But then you can check by some number theory that a times x is not equal to 0 in Zn. And that follows from the fact that you can get a control over the GCD of x and y up here. So I'll leave it to you guys to think about that. So what we end up with this is we have two non-zero numbers in Zn that are multiplying to something that is 0 in Zn, which tells us that m is a zero divisor. Okay, great. So I'm going to clean up the board and we're going to do a little bit more. So similar to what we just did with Zn, we want to classify all units and zero divisors of the ring of 2 by 2 matrices. And so this first statement I'm not going to prove. This is pretty clear from linear algebra. And so A is a unit. In other words, it has an inverse under matrix multiplication if and only if the determinant of A is not equal to 0. So that's part of the invertible matrix theorem. So I'm not going to go ahead and prove this. We kind of know that from a previous course. We're going to focus on the second one, which A is a zero divisor if the determinant of A is equal to 0. So let's suppose that A in M2 by 2R is a zero divisor. So let's see what that means. So that tells us, first of all, that A is not equal to the zero matrix, because being a zero divisor means that you're not the zero matrix, and there exists a B which is also not equal to the zero matrix, and A times B equals the zero matrix. Okay, good. But now, towards a contradiction, we're going to suppose that A has an inverse, and we'll call it A inverse. And now let's left multiply this equation by A inverse. So that'll give us A inverse A times B equals A inverse times this zero matrix, which is obviously equal to the zero matrix. But then A times A inverse will be the identity, which tells us that B is equal to the zero matrix. But that's a contradiction of this fact up here, and the contradiction arises from this assumption right here that A has an inverse. So what this tells us is that A doesn't have an inverse. In other words, the determinant of A is equal to 0 by the invertible matrix theorem. Okay, so that gives us this forward direction. Now I'll clean up the board and we'll do the reverse direction. Okay, so now we're ready for this reverse direction. So let's go ahead and suppose that the determinant of A equals 0. And so what that tells us is that the null space of A contains some vector V. So there's a bunch of ways that you can attack this. We're going to do it with this null space of A, but you could also do it using maybe the fact that if you have a non-invertible matrix, then two of the rows are linearly dependent, or the columns are linearly dependent, or something like that. So, but we'll use this one where we have a vector from the null space of A. Now the next thing that we want to do is form the following matrix. So we're going to form B made out of this vector. It is going to be the vector whose columns are made by the vector V. So it's just V and V. So notice that this matrix is not invertible. So this matrix also has determinant 0. And now let's go ahead and look at A times B, which is going to be A times this thing that we just constructed. Great. But then by matrix multiplication, that is AV, AV. Great. But by the fact that V is within the null space, we see that this is equal to the 0 vector in each column. Okay, great. But we know that this is not equal to 0 because we assume that v was not the 0 vector. And I guess we should also here suppose that A is not equal to the 0 matrix. So what we have are two matrices which are not the 0 matrix that product to the 0 matrix. So that tells us that A is a 0 divisor. Okay, great. So what we've done is we've classified all units and 0 divisors of this matrix ring. So I'll clean up the board and we'll prove one more kind of general result about units and 0 divisors. So we're going to finish this video off with the proof of these two observations. So if A in a ring R is a unit, then it is not a 0 divisor. And if A in R is a 0 divisor, then it is not a unit. So these are fairly straightforward. So let's look at the proof of the first one. So let's suppose that A in R is a unit, and that B is in R with A times B equals 0. Okay, good. So now what we'll do is, since A is a unit, it has a multiplicative inverse, so we'll call that A inverse. And what we'll do is we'll multiply both sides of this equation by A inverse. But A inverse times 0 is just equal to 0. And then we can reassociate here, and that will turn into B, A inverse times A, which is just equal to B. So notice what we gained here is we gained B equals 0. So it follows from that that A is not a 0 divisor. So what we did is we tried to make it a 0 divisor, like we created an equation that might allow it to be a 0 divisor, but we saw that that equation made the other member of that equation equal to 0, so it is not a 0 divisor. Okay, I'll clean up the board, then we'll prove this last observation, and then we'll be done. Okay, so let's notice that this second result follows from the first as a contrapositive. So I won't prove that. We kind of get that for free. So I'm going to leave you with the following question. And is it possible for A in R to be neither a 0 divisor nor a unit? So everything that we've seen in this video is that something is it is exactly one of a 0 divisor or a unit. We know that it can't be both by this observation, but can it be neither?